Hi, today I'm gonna show you my solution for a challenge from RomHack CTF. RomHack is a newborn security conference which was held in Italy in September 2019. And this particular challenge wasn't really hard, so it's a good opportunity to show you a project I'm working on, which is a Tools clone, but written in Python 3, which uses a Radare 2 to retrieve informations from binaries. It isn't already public on GitHub, but it will be sooner or later. The documentation is already outdated and partial, so it's better if I'll just show you how to use it. For this challenge, we were given a binary, so let's check what it is. It's an ELF file, so let's check what mitigations are in place. As you can see, there are no canaries, so we can overwrite the return pointer in the stack maybe, without worrying about cookies. The NX bit is turned off. This means that the stack will be executable, so we can put our shellcode directly in the stack. And it is a position independent code, so we're gonna have to deal with the ASLR, which is the only tricky part of this challenge. Let's try to run the binary. It just expects some input. Let's try a long input. This will crash the application. As you can see, we have a seg fault. So now what we want to do is we want to analyze the binary to understand what's going on. So let's open it with the Radare. We do some basic analysis and list the functions. Except for system functions, there are only main and a few more functions. So let's try to see the global call graph. So the main calls just two functions, and the first one may be the usual function that you see in CTF to set up the challenges, while the second one probably is the function which contains our vulnerability. Let's disassemble the main as expected. So now we can use the Ghidra decompiler to decompile the function. We can name it setup. And now the disassemble, as you can see, is updated. Now let's decompile the second function. Here, as you can see, memset is called, and then read is called, and it looks like that they work with different sizes, and the read size is bigger than the memset one, so probably we're gonna read our input in a smaller buffer. So we have a typical stack-based buffer overflow, which will happen in the vul function. So the return pointer saved on the stack will be this one, ending in E9. Since ASLR is in place, we cannot simply build a wrap chain to jump into our shellcode using any gadget that we want, because we don't know where they are, since we don't have a leak. But we can perform a partial overwrite, which means we will only overwrite the last byte of our return pointer, effectively hijacking the flow of the program. And so what we need is to find a gadget inside this range of addresses, which can help us to reach our shellcode. Let me switch to visual mode, and let's find some useful gadget. So we have a return instruction, but this gadget moves the stack pointer in the wrong direction because our shellcode will be before the return pointer. So let's move on. Again, here is the gadget, but moves the stack pointer in the wrong direction. Instead, this one looks promising. Let me highlight it. As you can see, this gadget will move the stack pointer effectively inside our shellcode and then jump to it. So we just need to have the right padding. We can put an op slide so we don't have to think too much. Then our shellcode and then the single byte to perform the partial overwrite. So let's take note of this value, C4. Now, first of all, we have to find the offset that we need to reach the return value. So to discover how much padding we need to put. To do this, we generate a cyclic pattern. We pipe it into the program. Now we can dump the core file. And then we'll analyze it with the core info, which is an utility from Pwn API again. We are interested in the first value on top of the stack, which is the saved return pointer, which is overwritten. And we find 120. So let's build our payload. We first need to know how long is the shellcode, which by the way is this one. We can disassemble it with the RASM2. So the shellcode is 48 bytes long. So we need 72 bytes of padding, 72 nops. I will put my payload in a file and then just pipe it into the program. First of all, the nop slide, then the shellcode, and then the single byte, C4. Let's try our payload. We need the second cat to keep the pipe open. It works. We got our shell and our flag. Let's try to run our exploit against the server. And again we get our flag. So now let me show you how you could achieve the same results but with scripting only. Again using Pwn API. First of all, we need to import the module. Then we set the logging level. And then we update our context with the binary file, remote host and port. Let me show you the difference between the different logging levels. So now I'm gonna do exactly the same steps as before, but through the scripting API. So first of all, we wanna find the offset. So we spawn a local process, we send to it a cyclic pattern, then we dump again the core file, we can analyze the core file with core, we extract the first value from the stack, which is the return pointer, and we compute the right offset inside our cyclic pattern with the cyclic find. And finally we move to craft our payload. We have to pad this with the nops. And finally we can move to run the exploit against the remote server. As you can see, the interface is really similar to Pawn Tools. And here is again the flag. Once your exploit is stable and reliable, you can again decrease the logging level to get a cleaner output. And that's all for today. See you next time.